What if every step you took was designed specifically for your body? Your pressure points, your movement, your needs? At Northeastern University, PhD researchers Jacob Miske and Emery, under the guidance of Professor Jeffrey Lipton, are rethinking how orthotics are made. Inside the Transformative Robotics lab, they are advancing a breakthrough 3D printing process that creates continuously tunable foam structures. This technology allows orthotic devices to be customized at a microscopic level, adapting stiffness, geometry, and durability exactly where the human body needs it most.
Hello, my name is Emery. I am a third-year PhD student here at Northeastern University, where my research project is on a process known as viscous thread printing, which is a process by which we manipulate material extrusion 3D printing to create stochastic foam in microstructures. And today we're talking about our company, In-Loop Orthotics, where we will use this process to produce custom 3D printed orthotics at a rapid timescale.
Hello, my name is Jacob Miske, and I am a third-year PhD candidate here at Northeastern University working in the Transformative Robotics lab. I am working with Brett and Professor Lipton to use viscous thread printing to produce these orthotic insole devices. Specifically, I work on testing these materials and devices to make sure that they are durable and able to withstand the forces present in the foot, ankle, and around the human body. We need to know this so that way we can produce devices that are actually able to help people, that can hold up to their use over a long period of time.
So with this process, we are able to create using a single thread, we're able to create a continuous 3D foam structure where we're able to locally tune the properties in order to create regions of higher stiffness or lower stiffness. And specifically within the context of using this to produce 3D custom orthotics, we're able to create arbitrary geometries in order to accommodate a variety of different foot structures. And then based on that person's specific needs, such as where their most significant pressure points or specific symptoms they experience are localized, we are able to tune the properties of the orthotic in that region specifically to address their needs.
Looking closer at this bar here, using the geometry and dynamic parameters of a die extrusion system, we can change the density of foams we're able to produce from high density down to a very low density that's squishy on this end and very rigid on this end. We can also create stack-ups of high density, low density, and high density again, make sure that the exterior of our bodies, our insoles, our orthotic devices are durable to scratching and pushing and shear forces, while also providing a nice soft compliance that people often need around the arch of their foot for support.
SparkFun really enabled us to do is spend that time developing this process and exploring additional application spaces. While we still believe orthotics is our main focus area, it enabled us to explore additional process aspects of this process that could enable different applications.
We needed to use the funds from the Spark Fund to test the crushability of our material, which was not covered in that initial research. The Spark Fund paid for us to spend that time to build those machines, to actually squeeze these materials millions of times in a very short time scale. Not just funding, of course, that'll be necessary at some point. This is a physical, tangible thing, but it's really the connections that we're going to need to make along the way. We're vendors, suppliers,
and obviously customers at some point.